Good afternoon, everyone. This is the Earth System Prediction Working Group meeting, so thanks for joining us. We're going to jump right into presentations, and then we'll have discussion at the end. A working group discussion. You can feel free to ask questions of the speakers for that kind of discussion around their science. We will start with the first speaker, who is Anisha Paul.
Hi everyone, I am Anisha Pal and I'm Scientific ML Engineer at Planet. And today I'll be talking about leveraging CSM2 data for machine learning based S2S forecasting. This work was done at Planet and each member of the Planet team has contributed to this project. So to start off, I would like to start by talking about AI foundation models. Like we have noticed in the past few years, AI has kind of become a household name, and majority of this success can be attributed to AI foundation models and their success in a lot of vision and language understanding tasks, as we can see here. And even though there's a lot of innovation in terms of the architecture that we see with these models, the main principle which has kind of propelled this advancement is this concept of pre-trained broad, but fine-tuned precise. And to briefly explain this, pre-training can be thought of as we have this like one machine learning model, and we have a large corpus of data. And what we do is we train the machine learning model on this large corpus of diverse data on usually a very simple objective, or sometimes an objective which is very similar to the downstream task. And through this kind of training process, we hope that the model is able to learn large-scale features, which helps it understand the downstream tasks, something like the foundational building blocks, which will help it understand those tasks that it needs to do in the downstream situations. And then because we have this model which learns these landscape features very well, we just need like very few data points for a task-specific application. We train the model on this and it converges really quick. So this is the entire concept which has kind of propelled the advancement of foundation models. And we have seen this in application with a lot of AI-based weather modeling as well, which is why we see that in the recent times, there are a lot of AI-based weather models which have advanced the skill in terms of weather prediction. And these models are mainly trained on ERA5 data, on hourly scale ERA5 data. And they are then able to perform a lot of multiple downstream tasks, ranging from downscaling all the way till storm tracking. So the question is, why can't we just extend what the AI-based weather models are doing to the S2S space? And the first problem is that of task complexity because of the interconnectedness between the multiple climate systems in the S2S space. And I won't go into this detail because this is a group of climate scientists, so I think I'll leave it at that. The next problem which we are mainly tackling in this work is the problem of data availability. So if you think about these AI-based weather models, then they mainly work in the hourly scale. But when we move in the subseasonal scale, we are either training on weekly or monthly data. And that means the scale of the data reduces by a factor of almost 100, right? Depending on what kind of temporal scale you're training on. And the final problem is that one can argue that since these models are doing so well in the weather scale, why don't we just extend them all the way to the subseasonal scale? And as these papers have also stated, that beyond a factor of like 10 days, there's a massive error buildup because they work on this auto-regressive rollout strategy. So to summarize, it's a much more difficult task because of these challenges that I just spoke about. So the one problem that we have tried to tackle here is the problem of data availability. And we noticed that this gap is basically kind of closed by Earth system model data. To give a basic one-on-one comparison, we have ERA5 data and we have CSM2 large ensemble. The first point is the point of the years that we have in ERA5 versus CSM2. And even though we have 1940 to 2024 data for ERA5, in terms of ML model training, we can only use from 1980 because of the uncertainty in the data before that time period. Whereas in CSM2, we have a large range of data that we are getting, and this also helps the model see a lot of different climate variations. Now, if we just do a basic calculation in terms of the number of months we get from each of these data points, then we can clearly see the difference over here. And then the number of ensemble members come in. So over here, just for the sake of one-on-one comparison, I've mentioned one ensemble member for ERA5, so please forgive me for any technicality. But when we do a basic maths, we see that in comparison to era 5 for S2S space, we have a much larger amount of data when it comes to CSM2 large ensembles. And now we can think about training these machine learning models to actually understand those large scale features on the pre-training kind of strategy that I spoke about in the earlier slides. So for our model, we used a very simple unital STM spatiotemporal model. And we did a deterministic quantile regression because our hypothesis was to understand how just increasing the amount of data can help break us into that S2S space. For our training data, we used CSM2 data from 1850 to 1922. We kept a separate test data, which was era 5, and we do comparisons between different model runs on this test data. We use a native CSM2 grid resolution, and we constrain the grid from -60 to 60 because for this simple modeling task, we do not want the complexities that CIs might introduce in this problem. So for our input, we have 11 variables, and as our output, we have temperature and precip for like a lead time of 0 to 3 months. And the metric we use for comparison is something we calculated called anomaly R-square, where we basically calculate the R-square metric over the precip and temperature anomalies. So in this case, the higher the metric, the better. So the first run that we did was training our model on era 5 data versus training our model on the CSM2 data, and then evaluating both of them on the same test set that I showed in the previous slide. And as we can see that the performance improvement is much higher when we train with CSM data. And one simple hypothesis here is that even though I know there's a lot of contention around CSM2 and ENSO, we feel that the CSM2 data actually helped the model learn these kind of large-scale features similar to ENSO, which it was then able to apply towards predicting better temperature anomalies. But the question was that, like, as I mentioned, that more data is always better, but is it really the case? So we did a little bit of ablation experiment where we increased the number of data points from 10 ensemble members to 25 to 50. And as we can see from this image, we kind of have like diminishing returns after 25 ensemble members. And one reason that can be is because this model is mainly learning the large-scale features. And with 25 ensemble members, it has kind of learned all the kind of large-scale features it needs to learn. So additional members are not really helping it with that kind of aspect. But that does not mean additional members won't help. Additional members definitely will help with the smaller scale patterns, which, given the simplicity of our model, it's not able to pick up. So the next step will be to introduce a more complex model, which we are working towards with our foundational model, NEVA, to be able to understand the smaller scale patterns, which will help push the performance of these models further. We also did some ablation studies to understand how different data normalization strategies can help with improving the model performance further. So we had 4 different normalization strategies across spatial and temporal axes. The first one is a global all-time normalization, in which case each variable has one mean and standard deviation. The second one is local all-time, in which each variable has one mean and standard deviation for each lat-long location. The third one is a month-wise global normalization, where we have for each variable, we have one mean and standard deviation for each month. And finally, we have month-wise local normalization, where for each variable, we have one mean and standard deviation corresponding to each location for every month. And we noticed that the performance is really a lot better when we do month-wise local normalization. And there are multiple reasons, but the main reason is that we see a lot of like variation in these variables, not only from a temporal scale, but also from a spatial scale. And given that the machine learning models work on the principle of a mode balanced data, if we do not have a distribution which is like more normal, if it's too skewed, then these models don't tend to do very good. So that is one of the reasons why we feel that having the right normalization strategy so that we can feed the right distribution to our model really helps improve the performance by a lot. And finally, I have this slide where we show for different lead times from 1 month to 3 months how our model does on predictions across temperature and precipitation. And as we can see from the graph over here, which is just a more quantifiable version of the slide I showed earlier, that our model obviously does a lot better in temperature compared to precipitation. And as everyone here knows, that precipitation is a much more difficult task, which we are also seeing with our AI-based prediction models. But what we do notice is that even though there's a drop as we go from like lead time 0 to lead time 3, the drop is not as sharply as we anticipated with these AI-based models. So that kind of gives us some kind of indication that we can extend them further to the subseasonal scale. So the major key takeaways is that CSM2 data can help create the next generation of AI foundation models for the subseasonal to subseasonal scale. And performance is very sensitive to the distribution of data, so picking the right normalization scheme might not be just normalization scheme, but ensuring your data is not very skewed when you feed it to the model is extremely important. And more data is definitely beneficial, but we need to scale the model complexity accordingly to be able to squeeze the maximum out of the model, out of the data. These are my references. Thank you, and I'm happy to answer any questions.
So we have time for questions. If you have a question, please come to the microphone. If you're standing in the back, there are seats in the front. Please come forward. And this is just like Southwest. If you have a bag sitting in the middle seat or the seat next to you, please remove it so someone can sit there. Thank you.
Nice talk. Thank you for that. I'm wondering what the ramifications are of training the data, or using the first 50 years or whatever, 70 years I think you used of CSM2 as the training data, and then validating it against a future climate period with like different radiative forcing, basically. Would you have gotten different results if you had trained, say, on the first 50 members of CSM2 in the present, and then tested against the second 50, for example?
Yeah, definitely. But then in the machine learning context, that would, like, we kind of get into the zone of this data leak, where we feel that the model has already seen those kind of patterns before. So it's not a very good understanding of how well the model understands the underlying physics to be able to predict what happens in the future. So
it doesn't matter if radiative forcing changes the patterns that are present.
So right now we are not seeing that. I think the concept is that, yeah, it'll definitely, like if I evaluate it on the exact same time periods, my performance will look a lot better because it has a more better understanding of the current time periods. But we also want to understand whether the model is understanding those large scale features which do not change as rapidly, probably. So, yeah.
Wondering, you talked about the quantity of data, but not necessarily quality of data. How important is it? I mean, the reanalysis product can be garbage as well, but it might be more valuable than other products.
Yeah, definitely. Quality of data is extremely important, and I think just apart from quantity, the quantity has to be diverse as well. So that is something that we need to focus on. But when it comes to these, as we have seen with AI foundation models, because these models are given so much amount of data that at one point, the quality does not matter as much because they're able to pick those large scale features, and that's what we are focusing on. So even if the quality is a little bit degraded, as long as it's able to pick out those large scale features, we can then do a fine tuning on higher quality data, which we are doing here, where like we are fine tuning on ERA 5 to get that quality factor in.
Thanks. Since you're training on CSM data, I was wondering if you compared to the skill of the initialized CSM simulations.
Yes, excellent question, and that's something that's been on our mind as well. We haven't done that evaluation yet, but we plan to. So, yeah, thank you.
So I have a quick question. We have a little more time, so I'm going to take a little prerogative to ask a question here. So you're talking about the large-scale features, and that implies some sort of reduced dimensionality state. And I'm just curious if you've sort of looked into what are, I mean, you mentioned ENSO, but what are these large-scale features, and how do they differ from what we kind of already understand about large-scale features that might lead to S2S predictability?
Yes, that's also a very good question, and that's something that we have in the pipeline. Like ENSO is one, there's MJO, there are other modes of variability as well. So we have that in the pipeline. We haven't evaluated it completely against that yet. Yeah.
Our next speaker is Paul Diermeyer.
Thank you. So yes, I'm going to talk about fidelity of land atmosphere interactions in CESM, since they are presumed to have a lot to do with subseasonal predictability. So just to review for those who maybe aren't so familiar with this part of Earth system and Earth system modeling, our notion is kind of our starting point is this one-dimensional picture of a sort of a local vertical coupling between land and atmosphere through water and energy cycles. So we've got this sort of chain of arrows and processes that we show on the right that basically assuming that the downward arrows are given and known. When it rains, the ground gets wet. When the sun shines, the ground gets warm. It's the upward arrows that are more subtle that we're trying to get at, those feedbacks. And so any broken links, any arrows that are pointing the wrong way or missing in the chain will interrupt any sort of land surface impacts on weather and climate predictability. And so where and when is our question. Are these feedbacks in place in the real world, and how strong are they? And then, of course, do our models get this right? So in the context of CESM, it's the bottom row of arrows that is the domain of CLM, the land model, and then above the surface fluxes, the arrows to the near surface states, boundary layer processes, cloud physics, and precipitation. That's the realm of the atmospheric model. So in its sort of most basic form, we are looking at the land state of soil moisture as a potential driver or control of surface fluxes. So we have here a schematic diagram, evaporative fraction that's on the y-axis over here. So that's just the ratio of available energy at the surface that's going towards the latent heat flux. So nominally between 0 and 1, but it can go outside of that range. And the x-axis is soil moisture, and we talk about there being these different sort of regimes of coupling between land and atmosphere. So, well, actually, let me go back. So we have a dry regime below the wilting point where essentially you don't have any evaporation. The water is too tightly locked into the soil. Above some critical soil moisture, it doesn't really matter when the soil moisture varies. Evaporation is occurring at the potential rate, and any variability in evaporative fraction is from other sources of the climate system. But in between, there is a sort of sweet spot where there tends to be a pretty strong and fairly monotonic increase in evaporation as soil moisture increases. And that is where the land surface has control in this transitional range over the surface fluxes, and that's the first step in the race towards this connection between land and atmosphere. And so because of this, soil moisture can regulate energy, net radiation partitioning only within a certain range, and those boundaries are different in different locations in the world. And the ability of the climate to move into or out of those different locations is expansive or limited in different parts of the world, and also by season. So we're going to look at some runs that Meg Fowler has done with CESM 2.1.5. There's land model only runs, and then coupled land atmosphere runs, no ocean, not fully coupled. 26-year simulations at nominal 1 degree, basically to diagnose the behavior, sort of stress testing the model. And so this is not getting at the S2S prediction skill directly, but at the characteristics that are necessary to harvest the prediction skill at subseasonal timescales. We'll also be looking at, for comparison to ERA 5, as Gokhan said, you know, it may be garbage, but there definitely are problems with even ERA 5 reanalysis when it comes to things like diurnal cycle, which are crucial for land-atmosphere interactions. But we will compare to that on its nominal 31-kilometer original Gaussian grid. And also for fun, we'll also look at MERA 2, at least locally at flux tower sites. We will do global comparisons as well as local with ERA 5. So for these local comparisons, looking just over continental US, there are, around the globe, very unevenly distributed, a large number of flux tower sites where we have meteorological measurements, radiation, soil moisture, surface fluxes, carbon even, all co-located. And over CONUS, there are several hundred stations, but about 60 to 70 that have long enough high-quality time series that we can apply to this problem. And the number varies from season to season, actually. But these are the places where we're doing our point comparisons. And we're looking to start with specific coupling metrics. First, very simply, Pearson's temporal correlation, correlations between soil moisture and latent heat, soil moisture and sensible heat, and then soil moisture and this evaporative fraction. We're also looking at the variability, standard deviations of each of those terms. And then we also have a coupling index, which is just the product of that correlation between a driver, soil moisture, and its response, say latent heat flux, for example, times the standard deviation of the latent heat flux, which is combining then this magnitude of fluctuation as well as the tightness of the connections. And so you could do this on any of those arrows that I showed in the diagram, but we're going to start near the surface and see if we can chain these together. Now, this horrible looking plumbing diagram, it looks like when Robert De Niro takes the panel off the wall in Brazil. This is what's going on inside of our models. Oh, good. People got that reference. I'm not that old. On the left, we're showing, this is a single site, and in fact, locally, Niwot Ridge Forest, not too far from here. On the left, we're showing what says OBS, but it's really ERA 5. Actually, the ERA 5 is supposed to be on the second side. I don't know why it popped down there, but on the left column is, so this is kind of a wiring diagram or a pipe diagram of all those arrows I showed you before, that little schematic. From bottom to top is land surface up into the atmosphere. The width of any line is the strength of that coupling index. How strongly is it coupled? And the arrow tells you what direction this coupling is going. The color goes from blue, negative correlations, to white, no correlations, to red, strong, positive correlations. And then the darkness of the green of each box is telling you the magnitude of that standard deviation. So there's a ton of information packed into these things. But what I want you to basically look at is on left is observations. ERA 5 is actually the second box. And then CLM coupled with CAM, and on the far right is CLM. So just to draw your attention to a couple of things, what we see in observations is that net radiation has a very strong control over sensible heat, and that's really driving the evaporative fraction in this location. Whereas we see, both in reanalyses and in CAM and in the CAM CLM, that's really not what's being portrayed. So we have an issue, and in fact, if you look in the very tiny small print, what you have is you have evergreen needle-leaf forest at this site, and ERA 5's grid cell says, oh no, we have broadleaf forest here. And even CLM has a mosaic that's mostly saying we have mostly grassland at this site. So land cover is something that can complicate and sort of mess up your simulations in these locations. But that's probably not all that's going on here. For instance, on the left side, though, you see something that's maybe more encouraging for the in-car crowd, is that we have this overcoupling of soil moisture to latent heat flux and evaporation in ERA 5, which we don't see in the observations, and actually CLM and CLM CAM, they match up pretty well in this particular location. So, you know, that's, you can really get into the weeds in this sort of picture, but we really want to back out and see what's happening on a larger scale. So Yoon Kim, my postdoc, put this together. This is actually showing across all of those individual sites in the US the seasonal cycle of the variation between soil water content at the surface, that's the x-axis, and down here, and evaporative fraction on the y-axis. And he has this weird sort of coloring scheme where March through August are the red numbers, and there's a line that goes from January to August, and December is a blue number. So you can kind of trace the seasonal cycle. And again, the labels got a little bit shifted for some reason here, but on the left side is what we see in observations, and we see that we have lowest evaporative fraction in February and the highest in late summer, and there's this little counterclockwise sort of hysteresis that goes on between these two, which is actually fairly well captured in CLM and CAM CLM. They both sort of reproduce that, and they have the seasonality phased right. When you look at reanalysis, it really is garbage. The timings are wrong, and in fact, ERA 5 is actually, the hysteresis goes clockwise, not counterclockwise. It's really not representing the process as well. Data assimilation might be messing with this in some part, and MIRA 2, I have no idea what's going on there. It's just crazy. All right, what we all call Yaga's paper, right? The Richter et al. 2024, where they found in CESM this lack of a response of atmosphere or even kind of ocean in terms of providing subseasonal predictability, matching the sort of infamous diagram here on the left, where we have this presumption that somewhere around 1 to 2 weeks, the land surface initialization impact should be quite strong. And we do see that in other models. In fact, even one that's really not all that great at land-atmosphere interactions, but it does show, CFS2, NCEP model, does show a kind of a peak around 15 days in terms of how the land surface is affecting, in this case, 2-meter air temperature. So what's going on here? Well, we can look globally now. We need to look at the big picture. Because and historically our notions of these coupling has come from looking at models. We haven't really had observations except at points like I've shown you, flux tower sites. So what we're trying to tackle is to produce a global picture of land-atmosphere coupling based on observations, or at least products that are as close to observations as possible, leveraging a lot of remote sensing data. And we'll be focusing only on this one arrow down here, what I've been talking about already, the soil moisture evaporative fraction, and see what's going on. So first of all, just to show you what the models look like before we bring in the OBS, on the left is this offline CLM run. This is this coupling index between soil moisture and evaporative fraction. On the right is CLM plus CAM, and on the bottom is the correlation part of the metric. So just the correlations of daily values in time during June, July, August is what's being shown here. So you kind of see these reddish blobs in places like the Great Plains of the US and the Sahel and India. Those are those hot spots, the Randy Koster famous hot spots, Ukraine, Eastern Russia, so forth, like that. So, okay, fine. We can compare to ERA 5. We already know this is model to model. It's not really telling us much about reality. So what can we do to validate these models globally and properly? Well, graduate students of mine, Nazanin Tawakali, has been working on this, looking at 3 soil moisture data sets that are all primarily satellite-based. They're not fully independent of each other, but they are based on daily observations. SMAP, the NASA product, CCI, which includes SMAP and many other satellite products, and then this SOMO.ml, which folds in a bit of machine learning as well to try and do some training on that. And 3 different surface flux products, which are, again, using satellite data and things that are not fluxes, plus various sort of machine learning regressions onto flux tower sites to infer surface fluxes. Fluxcom XBase, the Gleam 4.1, which actually in our test validates the best against in situ data, and Camille, which is kind of a multi-product ensemble. Everything interpolated to a 1/4 degree grid, 3 times 3, 9 ways to combine these. Because they're not totally independent, it's not 9 degrees of freedom, but we can get some picture at least of uncertainty by going this approach. And amazingly, oh boy, the lettering shifted again. Amazingly, there's a tremendous amount of agreement, a lot more than I would have ever expected. So this is showing our certainty about whether they're portraying all of a particular region in the same regime across all combinations of products. And any place where you see the cyan color, that's where there's a lot of agreement. So we think that we genuinely have things portrayed correctly. And the little red strips, which are only mostly a couple of 100 kilometers wide, is where we have uncertainties between this boundary between where the moisture limited versus the energy limited domains are. So you can come in and then say, well, gee, if your model has its transition zone somewhere near this line that's kind of running around maybe 95, 97 degrees west and sort of across Canada, and then along to the east along the Gulf of Cuba, then you're doing pretty good. So this is what the correlations now look like, just the correlation part. So SMAP, CCI, and SOMO on the top, everything correlated with the Gleam product that we think is probably the best. You see they all look very similar in patterns. It's just basically shifting where the 0 line is. SOMO tends towards lower values and more negative values in the tropics. SMAP has the least negative values. CCI, they screen out the very high LAI, so the rainforests are kind of masked out in that particular product. And then below that, we have CLM and CAM, CLM and CAM plus CLM. Very strong agreement on pattern among the observational products. And actually the models, not too bad. We seem to have quite good agreement with CLM. When it's coupled to CAM, then we kind of get too much positive correlation spreading out over too much area and too strong as well. For instance, look at Southeast Asia and China, which everybody, every model, every observational product says there's no positive feedbacks there, but CLM CAM is giving positive feedbacks of land and atmosphere in Southeast Asia. So coming back to the regimes, if we try to define these regimes now, so you know, we have our sort of 3 legs in our sort of linear diagram here, and so we can characterize that between, is any location occupying 1, 2, or all 3 of those regimes based on its sort of climatology. And this is This is based on the SMAP versus gleam. So the colors tell you, are you in the wet regime only, in the transitional in the wet, et cetera. And the little bar chart tells us from observations what we feel is going on based on those products. And what we see is that as long as you have anything that's on the left of the critical soil moisture line, that means the land surface has an ability to give a feedback. Through the moisture and energy cycles in the transitional regime or in the dry regime, that's where we have extreme heat cases where we get this really positive heat wave feedback can occur, even though the water is maybe not playing. And we see that more than half of the globe seems to have some sort of a land surface feedback connection going on. And if we look at the models, not too bad, but one thing that we do see in both CLM and CAM is that, one, they have too much of the area that just sits always in the transitional zone and not enough area that ever gets into a dry regime. You don't see the red and the yellow and the cyan showing up, which would mean this model maybe is going to struggle with forecasts of extreme heat. And zooming in on North America, you can kind of see, oh, do we have that boundary in the right place? CLM, not too bad. CAM, the blue is too far to the east. And anyways, but it gives us something we can really start to validate our models with. So summarizing, we're beginning to look at these coupled feedbacks in CESM. There's still a lot that we can do. And a really key resource is going to be these observational estimates. Something I haven't mentioned, but it's sort of another elephant in the room is vegetation, which can exert a lot of control and is not typically part of this water and energy cycle view, but carbon plays a role as well. And so we know CESM does a lot of carbon. So I'll leave it there. Thank you, Kathy.
All right, in the interest of time, we will not take questions right now. Please do ask Paul questions when you get a chance after or during discussion. If you'd like to talk more about the land-atmosphere interactions, we can do that. Our next speaker is Judith Berner.
Hello. It's great to be here. I'm going to talk about benefits of online bias correction versus post-processing. So subseasonal to seasonal forecasts have generally very little skill, except so-called windows of opportunity where temporary skill emerges. Here we study the impact of an online bias correction on forecast skill and compare it to a posteriori bias correction. The problem we have with our S2S system here at the CSM S2S suite is that we don't initialize it from reanalysis that have been generated by the same model, but we initialize it from foreign initial conditions. And so we have a drift in our system. And to deal with this, we need to remove the lead time dependent bias, which typically requires a large set of hindcasts. Systematic biases reduce forecast skill, so Abby will talk, it's the next talk, which maybe would have been much better after Paul's talk, but that's fine. So why do we need an online bias correction? So here sort of is my attractor. This is actually a attractor of CSM, but the idea is that if we have systematic biases, let's say the SST is just too cold, let's say over the North Pacific or the North Atlantic, it's systematically too cold, then we can never spin off a hurricane. And so there are certain things where we cannot do a posteriori processing to get at the right skill. So the idea is that you need to be on the attractor, you need to move the model to the right side of your slope so that the dynamics which is in the model can spin off and produce the right results. The experiment setup, so this is a version of the S2S suite here at NCAR. So it's the coupled climate model, it's 1 degree horizontal resolution, follows the SubX protocol, which means weekly initializations from 1999 till 2022. We initialize from NCEP CFS. So this is basically we take one reanalysis, and then we use anomaly initialization. So typically January 1st anomaly on top of January 1st initialized forecasts to come up with an ensemble. Here is my portray of the lead time dependent model bias. So here we see a model error. So here we see different weekly initializations. We see the observations. And as we initialize, the model can fill the model attractor, which is sort of here schematically by the red line. And so in addition to the forecast, the model drifts towards the model attractor. And so this is one reason why we have this lead time dependent bias. And so this happens in S2S forecasts, and it's even more extreme if we have initialized decadal forecasts, where it can be really 10 years or more before the system is done with this spin up and actually makes a good forecast. One reason why we do have skill forecasts is that we remove this lead time dependent bias, and that makes our forecast a lot better. And this is great. We want to have very skillful forecasts, but there is a big part of model error that we never see because we're systematically removing systematic biases by looking at correlations. That's the point of the talk. Okay, so just to quantify this, here is week 1, 2, 3, 4, and 5, 6 forecasts for 2-meter temperature. This is just a global mean. And so in blue is shown the model after removed the lead time dependent bias, and in red, the original raw data. And so we're getting like about a 30% reduction of RMS error if we remove the lead time dependent bias. This is great, but this is model error we have that we should address if we want to improve our models. Here, this is some work by Will Chapman and myself, where we came up with an online model error correction based on nudging tendencies. So where we're nudging the CSM towards error 5 data, we took a big library and came up with a systematic effect. We did a number of simulations based on nudging, stochastic and deterministic versions, and also using data assimilation increments. Those are these different colors. It's stratified by the season. But what we found is that the RMSE is improved globally by 10% for 2-meter temperature and up to 40% for sea level pressure. This improvement was there in all surface variables, but also if we look at the free atmosphere, most of the things are improved with the exception of a few things like the moisture profile. So this is published, and so now what we wanted to do is, so this was done in climate simulations, in 30-year simulations of a free-running climate system. So now we wanted to see, well, if we put this into our forecasting systems on the S2S timescale, by how much can we improve the skill? So here, this is root mean squared error. And so here in the shading, the light shading is the root mean squared error for 2-meter temperature left and sea level pressure on the right side. If we remove the lead time dependent model bias, then we get the solid contours. So again, we see sort of this roughly 30% improvement in RMS error if we remove the lead time dependent bias. And if we look at the difference between the red and the blue, it tells us how much more having an online model error correction improves skill. So these are small numbers, but we can further improve the skill by having an online model error correction while we run the model. This is the ACC. So we see here the anomaly correlation. Again, in solid, we see the improvement by having an online bias correction out to weeks 5, 6 for both 2-meter temperature and sea level pressure by about 10% or so. So it is beneficial, but it is small in comparison to removing the lead time dependent bias. This is the end. So I just wanted to show you some pictures of this. So the bottom is the difference with and without removing the bias. And we sort of have the same problem, which is that we can look at the pictures and maybe make some assumptions. For example, it seems something is going wrong over the warm pool. Obviously, the southern oceans are not well captured, and so this is where introducing that model error correction is really helping, but more work is needed to then really feedback and make the model better. Thank you.
How much of a cost does it add to do the online bias correction, and do you think it's worth it for those changes?
Yeah, so it's very cheap. So what we're doing here is basically reading from a library. And so these nudging increments are stratified by time of the day, and there's a seasonal cycle, and you can do it deterministically or stochastically, where you can put in a typical January 1st anomaly on top of it, so it's very cheap. But Will has done some more work where we actually go a step further and rather have the nudging increments. We're machine learning those. So then we have a state-dependent online modular correction, which, for example, helps with the MJO. And this one is also pretty cheap. So we can run this really fast thanks to the great collaboration with the software engineers.
So one benefit of having the online would be, I guess, if your errors are non-stationary, do you see like times or places where the online correction is maybe contributing especially well, or is it mostly this kind of blanket several % improvement?
That's a great question, and I haven't done the analysis to say this, but we know that the state-dependent version learned on the nudging tendencies is much better than just putting the nudging tendencies back in. So I would assume there is a state dependence, and this is exactly what we hope machine learning to do, is get that state dependence in.
The question is, do you have to still do the de-drift post-processing even when you use the online nudging?
Yeah, so those are these plots. So the light versus the solid tells you how much removing the lead time dependent bias gives you. So this gives you 30%. It gives you a lot of skill, both in, this is RMSE, but also in ACC. It's the next plot, also in ACC. And then the difference between the online bias correction or not is blue versus red. So what we're doing is really, really small in comparison to removing the lead time dependent bias. And so there's still lots of work to do in our initialized forecasts, and Abby will address some of these issues in the next talk.
Well, it's clear that our next speaker is Abby.
Hi, I am Abby J. I'm an associate scientist in M-Cubed. So this is my first CESM workshop. It's very exciting. Yeah, even though I didn't stand up yesterday because I was lazy, let's say. All right, I will be talking about looking at sources of subseasonal prediction skill in CESM within a perfect modeling framework. And in a perfect modeling framework, instead of comparing to verification, like observations, we're comparing to a member of the model, just an ensemble member. So this is based on work that Richter et al. Did. It was published in 2024 that investigated the sources of subseasonal to seasonal predictability from initializing the ocean, atmosphere, and land components. So they did multiple different runs where each component was taken out, and you can see like what the impact of the initialization was. So they did see that initializing the ocean adds limited predictability on the S2S time scale. We need more time there. And then also initializing the land deteriorates the scale on the S2S time scale, which is not great. These results pointed to some possible problems with the initialization drift or spin up and coupled model drift. So again, here we're going to repeat the analysis, but in a perfect model context, where we can eliminate the model error, but not the initialization drift. So just quick, this is the same kind of setup that Judith talked about. We're using CESM2 at 1 degree horizontal resolution in the atmosphere and ocean. And we have weekly initializations, 1999 through 2022, initialized each Monday for each month. And they follow the sub-X protocol with 11 ensemble members initialized from CFSV2 using an anomaly initialization. So prior to verification, the lead time dependent bias is removed, and then model error does arise from shortcomings in the parameterization schemes and in the interactions between the model components. So you've seen this before, just a few talks ago. So this is adapted from Diermeier's paper, but it was in Jager Richter's paper in 2024. It's a hypothesis on what the impact of the atmosphere, land, and ocean, initializing the atmosphere and an ocean is on predictability. So, but here we want to quantify the value of these initializations. We quantified it by replacing the land, ocean, atmosphere with their climatological counterparts, and then we verified it against the fully initialized simulations to see exactly, like, just like removing a variable and then seeing what impact that variable has on the model run, on the performance. So this is from Jaga's from Jaga's paper as well. So this is annual temperature, 2-meter temperature, ACC over the northern hemisphere mid-latitude, so it's 30 north to 60 north. So on the right, we're comparing the CESM hindcasts to CPCA temperature observations. And we can see that the hypothesis did not come to be. The atmosphere has the biggest impact, obviously, in weeks 1 to 2. But after that, we see that the initializations of the land and the ocean don't really have much impact and can be detrimental. So in this figure, I'm showing ACC for weeks 1 and 2 and 3 and 4. Those are the columns. And the rows, I have CSM2, like the original run at the top. And then the one, the Climo land without the land initialized from climatology. And then I have a difference plot at the bottom. So that's the original run minus the Climo land run. And it is somewhat hard to see with these projectors, which is unfortunate, but it is mostly blue, which is not great, which means that initializing the land is detrimental to the performance of our model run. So to address this and kind of like get some more information about what's happening in these runs, we're going to repeat the verification in a perfect model framework to eliminate the model error. So here I added one more figure on the right. So this is looking at it where I say that the observations are just like ensemble member number 10. I just chose one at random. So we can see that the atmosphere does play a similar role as in the previous ones, but the land plays a much larger role. It does increase the skill significantly, and the benefits grow throughout the S2S range. So the benefits from initializing the land are markedly higher than in the ocean and the S2S range, looking at it in this way. And this can point to a coupled model error between the atmosphere and the land as an essential problem in these simulations. So here we're looking at the 2-meter temperature ACC skill in the perfect model for JJA and DJF, so 2 different seasons. And then again, I have CESM2, the Climo land, and then the difference in the bottom. So we can see that initializing the land is beneficial when looking at it from this perspective. Scale is added, especially in the tropics and the summer hemisphere in the bottom left. But in general, there's more red than blue in these figures. And just to like hammer it home here, comparing the perfect model to the verification with observations, you can really see the differences here, and that initializing the land is important when looking at it from the perfect model framework. So I made this talk for EGU, and the talks were much shorter, and I needed to add some content, so I just looked at precipitation as well. So the scales on these figures are different. So it is still really red, but the scale is much lower for ACC. So looking at seasons again, this is JJA and DJF, and the same rows. But we can see that, again, initializing the land helps precipitation, but on a more regional basis. Looking at northern South America and kind of northern Europe, especially in JJA, but it's a more regional basis. And then also, I'm not quite sure what's going on in Africa in DJF. That's something to look into as well. And then comparing these to the verification with observations again, you can see that there is a very large difference when looking at it from the perfect model. And then if anyone's curious, I also made these like line plots for ACC. So looking at it, comparing to observations, we see that everything is quite low, including the atmosphere, which we know. But in the perfect model framework, there is some improvement when looking at the land initialization. And this is like this is the best performing area I tried. I looked at a few different mid-latitudes all over the world, but this is over the tropics, 30 south to 30 north. And then also with the ocean, not surprisingly, initializing the ocean doesn't help early on, but it does improve after a few weeks. And then in conclusion, I'll just like summarize what I talked about. YAGA in 2024 investigated the sources of predictability from initializing each of the three components. And it was found that initializing the ocean and land is not as beneficial as we thought when verifying against observations and reanalysis. So here we repeated the analysis, but verified against an ensemble member instead of observations. And in the perfect model, we saw that initializing the land does add significant skill, and the benefits grow throughout the S2S range. So again, this points to coupled model error between the atmosphere and the land as an essential problem in our simulations. And that's all I've got. Thanks.
Oh, that was very interesting to see. I mean, kind of hopeful in a way.
Yeah.
I don't quite understand why you come to the conclusion that it's a coupled atmosphere land model error problem as opposed to an initialization problem, because it seems like by doing the perfect model simulation, model against model, how do you come to that conclusion? Let me just ask that.
I'm gonna ask Judith to answer that because I don't know. I think she would have better.
Okay, well, there might be yet one more set of experiments where we could separate those two, but yeah, we can talk about that. Yeah, with this framework. Yeah, okay, thanks.
Yeah, that'd be super interesting talk. Trying to figure out or think through what properties of the land surface might be responsible for this. Do you think it's, for example, getting the soil moisture and the moisture in the soil system correct, because so much precipitation is due to recharge the atmospheric moisture from evaporation from the Earth's surface, so that could have a big impact on storm systems over land. Do you have a sense of which properties of the land surface are there some that are more important than others in this context?
I mean, I would definitely say it's soil moisture, at least with my perspective, is like the most important. And I'm doing some tests with Meg on this data right now, where we're kind of doing some state-dependent work based on different states just over North America of how wet and how dry it is, seeing how these perform in those respects and how big of a deal it is.
Does initialization also affect evapotranspiration rates? Do you know?
I don't know. I would think, but I'm not sure.
Thank you. Very interesting results.
Thank you.
I have a question. I tend to think of this perfect model stuff in the context of getting the signal and the noise correct. So I'm wondering if maybe you can help me think about this in the context of a signal to noise. So if the model's very good at predicting itself, does that mean it's misrepresenting the signal? Like if it's much better at predicting itself than it is in predicting the real world, does that mean, is that in itself a sign of model error, that the model has is sort of maybe too persistent, or there's some error that makes it really good at predicting itself compared to the real world? Or is there some issue of not getting the noise correct that sort of is affecting that signal to noise ratio as well?
I have no idea. Again, Judith, I don't know if you have anything.
CSM is very under-discursive in the topics. This is why we need to have So, yes, it gets, the reason that the skill is so good in the tropics is because the ensemble is
Yeah, I mean, I think that, to me, that points to some sort of model error in itself, that when the model is really good at predicting itself. And I think I personally feel like we have to be careful about this perfect model assumption, because making conclusions on this perfect model assumption when we know, in fact, our model is not perfect always makes me a little nervous.
Question about the perfect model approach. I think I read that when you compute the model scale in the perfect model setup, the choice of whether or not to include the member that you choose to verify against makes a difference. Like, I'm curious, like in your approach, did you include or exclude that member for verification?
I just chose a member at random.
Yeah, but then when you verify against that one member, for example, you have 11 ensemble members, right? You choose one as verification, and then when you calculate the scale, do you use the rest 10 or use the 11 total?
I removed that member.
I see.
Yeah.
I'm just curious about that.
Mm-hmm.
Really cool work. I was wondering, it looked like the anomaly correlation coefficient was increasing as a function of lag time with the atmosphere initialization, even in the perfect model.
Mm.
Can you comment on that? So that's a kind of a difference from what you might expect in the theory picture. Yeah.
So can you explain your question again?
Yeah, so on the far right, this is the perfect model experiment. And so if you look we might hypothesize that the predictability is highest at the shortest lead times when you initialize in the atmosphere. But in fact, we see that we have higher predictability a few days out.
Mm-hmm.
And I'm just wondering what might cause that.
Yeah.
In a perfect model.
Yes, because so verification against an ensemble member that is still initializing from how CSM is initialized.
Oh, okay. Yeah, okay. Thank you.
Yeah. All right, thank you.
Right, our next speaker is Isla Simpson.
All right, thanks. So this is going to be about the impact of vertical resolution on seasonal prediction skill in CSM2. So this is a project in collaboration with CW3E at Scripps. They had the computing time that made this project possible. So here you're seeing the vertical grid for the standard version of CSM2. This is the grid that was used in the original SMILE ensemble that was led by Steve. And what we're doing here is going to compare prediction skill in simulations that use this grid with skill in simulations that use this red grid, which is the new grid for CAM7 almost, except it doesn't have changes in the boundary layer. So CAM7 is going to have a higher model top, an 80-kilometer top, and enhanced vertical resolution in the troposphere and lower stratosphere. And so we're looking at the impacts of this new grid on seasonal prediction skill. So we have two new seasonal hindcasts, one with the original 32-level model and another with this 83-level configuration. These are both using CSM2 with no real physics changes. They're following the same protocol as the original SMILE, but one difference is we're initializing from ERA 5 because it goes high enough up. And here I'm just going to focus on the November 1st initialization and compare the skill between the 83 and the 32-level model. So I'll show some skill metrics. In each case, we're going to remove the lead-dependent climatology. I'll show the anomaly correlation coefficient, so a value of 1 is perfectly correlated, 0 is not correlated. That doesn't necessarily tell you whether you're getting the magnitude of the signals right, so I'll also show the mean squared skills score relative to climatology. So a value of 1 is there's no error, value of 0 is you're not better than climatology. So if we're going to have skill on seasonal timescales, it's going to come from slowly varying boundary conditions on the troposphere that are predictable. So ENSO is an obvious example. But the QBO is also a slowly varying boundary condition. So this is an oscillation of the equatorial zonal mean zonal winds in the stratosphere with a period of about 28 months. And if we can predict the QBO, and if it has impacts on the troposphere, we might expect that predicting the QBO would lead to some skill on seasonal timescales. So first of all, here's the skill of the QBO. So this is showing equatorial zonal mean zonal wind. We've got anomaly correlation coefficient on the top and mean squared skill score on the bottom. So this is for the 32 level model. And so it has skill in the lower stratospheric winds, but it kind of falls off pretty rapidly with lead time. This is with the 83 level model. And so you can see we have way more skill in the QBO with this new vertical grid, and that's the difference between them. And that becomes very clear if you look at QBO composites. So here's the composites of westerly and easterly QBO in ERA 5 reanalysis. That is what it looks like in the low top model, and so you can hold on to the lower stratospheric winds for a bit, but you're really not capturing the structures with the low top model. And then in the high top model, the 83 level grid, we do a way better job at capturing this seasonal evolution of the QBO. So now that we can predict the QBO, how does that impact on skill and things we might care about? So here we focused on features that have been argued in prior literature to be connected to the QBO. So there's been argued to be a connection with the Northern Hemisphere polar vortex, the North Atlantic Oscillation, Madden-Julian Oscillation, tropical precipitation, tropical easterly jet, and the subtropical jet in the Pacific sector. In the interest of time, I'm not going to talk about these three other than to say there's no skill improvement. In general, this is going to be a talk that is filled with disappointment, but I'm actually more interested in the role of the QBO and potential predictability than I was before we started. So hopefully I'll convince you of that by the end of the talk. So let's start with the Northern Hemisphere polar vortex. So the Holton-Tann effect says that during westerly QBO, the Northern Hemisphere polar vortex is stronger than during easterly QBO. And you see that here in this observation-based composite. So now that we can predict the QBO, do we see that manifest in enhanced skill in the Northern Hemisphere polar vortex? So here's the skill in DJF average zonal mean zonal wind in the low top model, and you can see that we have no skill in the Northern Hemisphere polar vortex. So does this look better now that we have prediction skill in the QBO? This is what it looks like with the 83 level model, and you see we still unfortunately don't have skill in the polar vortex, and that's the difference between them. So even though we have this much improved skill in the equatorial zonal winds, that doesn't seem to appear as skill in the polar vortex. So why might that be? Is the Holton-Tann effect just not a real thing, or are we not representing it correctly? So here I'm focusing in just on January, which is the month when in the observational record that link between the QBO and the polar vortex tends to be the strongest. So you've got here in ERA 5 a correlation of about 0.5. In the low resolution model, we have a correlation of 0. The nice thing about these initialized hindcasts is we can do some sampling. So for every initialization date, we have 20 members. And so we can just randomly select individual members from each initialization date, string them together, get a single member time series, and ask what is the range of correlations you can get between the QBO and the polar vortex with these single member samples. And so when you do that with the low top model, that's the range of correlations that you can get between the QBO and the polar vortex. And you can see that you don't reach the value in reanalysis saying that something is going wrong in this low top model. So what about the high resolution configuration? That's the range of single member correlations you get in the high res configuration. And so it's a little bit more positive, but you still don't encompass ERA 5, again, suggesting we're not doing something right. But if you look at the ensemble mean correlation in this high top model, you do get a correlation that is as high as what you get in the reanalysis. But we've had to average over 20 members to get that. So it's kind of pointing towards maybe a signal to noise issue. And so if we have that correlation, why don't we see that as skill in the polar vortex? And I'm still, I think, trying to get my head around this fully. But I think it's because this is a small signal. There's a lot of unpredictable variability in the polar vortex. But it's also a smaller signal in the model than it is in the reanalysis. So if instead of doing a correlation coefficient, we regress the polar vortex winds onto the QBO, you have a much higher regression coefficient. So kind of the slope of that relationship is bigger in reality than it is in the model. Again, maybe suggesting that we have a signal to noise problem in this relationship between the QBO and the polar vortex. So now I'll move on to the MJO. So this has been argued to be connected to the QBO. This is showing a metric of MJO activity. It's the standard deviation of MJO filtered OLR. So in the climatology, you've got a bunch of MJO activity here. And then this is the difference between easterly and westerly QBO. So in the observational record, easterly QBO is accompanied by more MJO activity. Here's what that looks like in the low top model, and we don't capture that signal. And so now what does it look like in this high top model where we have good skill in the QBO? Unfortunately, we still don't have the QBO MJO connection. But we can do our sampling game again, and we can pick out this maritime continent region. Here are ensemble mean differences in the MJO between easterly and westerly QBO, and there's ERA 5, and we can ask, do we get any individual member samples that give you as big of a difference as you get between easterly and westerly QBO as you get in ERA 5? And the answer is no, there's not a single one of these 1,000 bootstrap samples that does that. So this is just building on, I think, what we already know, that models seem to be failing to capture this connection between the QBO and the MJO, but doing so in this initialized framework where, of course, all the ENSO aliasing and things is, you don't have to worry about it because these are initialized. Okay, I'll finish up with the subtropical jet in the Pacific sector. So here you're seeing in ERA 5 the difference between westerly and easterly QBO. And of course, there are many other factors like ENSO and things could be going on here. I've always been a bit skeptical about whether this is really a signal related to the QBO. But if we average over the longitude sector of the Pacific, this is the latitude height structure you get. And it's definitely tempting to think of these as kind of being tendrils of zonal wind anomalies coming out of the QBO and teleconnecting to higher latitudes and lower altitudes. So now that we have this good skill in the QBO, do we see improved skill in the upper tropospheric winds in the Pacific sector? And so here's the skill of upper tropospheric zonal wind in the low top model. Here's the high resolution model and the difference between them. And again, we do not have improved skill by representing the QBO. That's because you don't see this difference between westerly and easterly QBO in either of these configurations. But if we look at our latitude height cross-section, I'm kind of struck by how much more similar to reality the 83 level model looks. It just is kind of a lower amplitude. And so is there a chance that this observed signal is really a real QBO signal and the model is kind of trying to do it but just doesn't have the amplitude right? And so what we could do is take out the QBO part. We have a pattern correlation of 0.75, so that's pretty high. And we could regress this ERA 5 pattern onto the model ensemble mean. And then we can do the same with all of the individual single member samples and asked, is that pattern regression coefficient higher than what you can get by regressing the model against itself? And so that's kind of maybe like a signal to noise paradox metric, but in the form of kind of a teleconnection pattern. So here's the regression of ERA 5 onto the ensemble mean. So it's kind of saying that the pattern is like 2.5 times higher amplitude than the model ensemble mean. And now we can look at individual member samples taking the model and regressing it onto the ensemble mean, and that's what you get. So there's a very small chance in the model of getting a pattern that is as correlated and as high amplitude as era 5, but it's like a 1% chance. So I'm kind of 99% confident that the model, that maybe the real signal is bigger than what we get in the model. So I'm probably out of time. I will leave my conclusions up and take any questions if there's time.
Hi, Isla. Thank you. That was really great. I'm wondering if the connections between the QBO and these other places could not just be limited by the vertical resolution, but also the horizontal resolution of the model. Have you guys thought about kind of a high resolution version of Wacom?
Yeah,
high top, I guess.
Yeah, I think it would be really nice to try that. Now that I'm a bit more convinced that there maybe really is a stronger connection going to higher latitudes, I think it would be good to see if in higher resolution, like, do you get the wave breaking and its response to the QBO more correct? Maybe gravity waves, like, do we need to resolve them to get this correct? Yeah, I definitely think it would be good to look into when we have higher resolution CSM3 with this high vertical resolution.
Thanks.
Thanks, Isla, for the talk, and kind of following up to what you just mentioned with gravity waves, I wonder how these different vertical resolutions differ in resolving Rossby waves and gravity waves in general, and whether they're propagating more downwards or they don't have that propagation to have these types.
Gravity waves or Rossby waves or both? Or?
No, you mentioned gravity, but I was wondering about Rossby waves. That was my original question. Like, are they different in this when you add the vertical resolutions?
Yeah, they definitely will be. Like the polar vortex is, a lot of it is in the sponge layer in the 40-kilometer top, and so that's definitely messing with the planetary waves and their interactions with the polar vortex. Whereas in the 80-kilometer, they can freely go up and interact more. Yeah. Yes, I think it's probably the model lid is the biggest impact of this, the change in the grids on the Rossby waves would be my guess.
If you could do a similar dynamical statistical correction that you did in your earlier paper where you teleconnection and see if you get better polar vortex skill just from sort of the predicted pattern that you amplify.
Yeah, I think that's a good idea. Yeah, I guess, how confident we are in the magnitude of the connection and reality, I think is a question, but if it does give us more skill, then we might as well do that. Yeah, that's a good idea.
Thanks so much, great talk. So now that you thought about the signal-to-noise paradox in this context, how do you think about the classical one with the NAO and the North Atlantic? How do you think about it now? Is it sampling, or do you think it's more than sampling? Thanks.
I think in the UK Met Office model, it's not sampling. I think they've kind of done that test that we don't have a signal-to-noise paradox in the NAO because we don't have much signal. But I do wonder if it's related to this. I mean, I think there have been papers from the Met Office that have argued for a role for the QBO in the NAO signal-to-noise paradox, and I do think there's potential for that. Do you not agree that we don't have a signal-to-noise? Oh, okay, not like the DJF, the seasonal DJF predictions from November don't have a signal-to-noise issue.
Next talk is Evan Meeker.
Hi, everyone. My name is Evan Meeker, and I'm a graduate student at the University of Wisconsin-Madison. And for anyone that was expecting a marine heat wave talk, come talk to me afterwards. I got some cool plots. But today I'm going to be talking about a relatively simple way to test for prediction skill differences between models while accounting for the correlation between them, using Smile's predictions of the PDO as an example. And I've already seen a couple talks today where I think this test could have been applied to give you some significant skill. So I hope folks here find this useful. Thanks to my advisor, Liz Maroon, and to my collaborators for their support, and thanks to NSF and NDSEG for funding this work. So this presentation is based on work from my first paper, which is currently in revision at GRL. And one major takeaway from it is that there's a seasonal dependence for PDO prediction skill in SMILE. So here I'm showing SMILE's ensemble mean PDO prediction skill for each of its initializations, February, May, August, and November. And on the x-axis, I'm showing lead time, monthly lead time, and on the y-axis showing prediction skill calculated with anomaly correlation coefficient. You can see that the SMILE predictions for the PDO are skillful at fairly long leads, staying above 0.5 for all initializations out to lead 13. And you can also see that there's some seasonality in the PDO predictions, which becomes even more apparent when I add an offset to these lines. And so this is now the same thing, but I've added a 3-month offset to the May line, a 6-month offset to the August line, and a 9-month offset to the November line. And the thing I want to point out here is that for the February initialization, you have about the same skill the following February as you do for the November initializations, even though the November initializations are only at a 4-month lead. In the paper, we also used a suite of linear models. To dig into the relative influence of local initial conditions and tropical Pacific forcing on PDO predictability. The simplest of these models is a first-order autoregressive model, which is also known as a damp persistence model or a red noise model because it generates time series with red noise spectral properties. So this equation is easy enough to understand. The value of my modeled PDO at time t is equal to the value at t-1 multiplied by a regression parameter alpha. There's also a white noise coefficient here, but for the deterministic prediction, that's zeroed out. So for the best fit AR1 model, alpha is estimated by the lag1 autocorrelation, which in the case of the PDO is 0.91, which is quite high. So for example, to predict the PDO for comparison to SMILE's February initialization, I would start with the February PDO, multiply it by alpha to get the March PDO, multiply it by alpha again to get the April PDO, and so on. And then I can calculate the ACC in the same manner as for SMILE, and this is what it looks like. And this is what the comparison to SMILE looks like. So the blue line here for the February initialization is exactly the same as I showed earlier, and now we can compare it to the AR1's model prediction skill. We see that the SMILE PDO predictions perform substantially better than the AR1 from leads 4 through 13, and then fall more in line with the AR1 skill at lead times beyond the following spring. Unfortunately, substantially better wasn't quite good enough for reviewer 2, which is fair enough, because this line plot's kind of begging for some confidence intervals. So how do I quantify the uncertainty on my prediction skill? Well, calculating the confidence interval is pretty much stats 101. Any package in Python or whatever your coding language of choice is that can calculate an R value should be able to calculate the uncertainty right along with it. So for a 95% confidence interval, here's what that looks like. And those bounds are a little bit wider than I was hoping for, and that's only the uncertainty on the SMILE predictions. So when I add the AR in, this is making substantial sound a little bit silly. And to be clear, what I would like to see is the confidence intervals for the SMILE predictions and the AR1 predictions either not overlapping or overlapping by a very small amount to be able to say that they're significantly different. And an explicit test for the difference in correlation isn't exactly the same as looking at these confidence intervals, but I've also run that test, and it comes up insignificant for all lead months. But this doesn't feel right. My intuition regarding prediction skill is that even small improvements are meaningful, but this seems to be saying otherwise. So am I doing something wrong here? Well, it turns out my intuition is correct, and the problem with the standard significance test, and with the way I was interpreting these confidence bounds, is that they assume that SMILE and AR1 predictions are independent samples. But because the models are both verified against the same observations, the predictions are not independent. That is, the predictions from each model will be correlated with one another, leading to biases in the standard test. So what test should we use? Well, we'd like to use a test that explicitly accounts for the correlation between models. And luckily, people have been thinking about this problem for a long time. So this equation that I'm showing here is a test for significance difference between two correlations, which depends not only on the correlation between each model and the observations, but also on the intermodal correlation, which is RAB here. The test statistic, T2, has a student's t-distribution with n-3 degrees of freedom under the null hypothesis of zero correlation difference. And the way that this is different from the standard test, so we have, let's see, we have RAB in the numerator here, which would go up as your intermodal correlation is higher, but we have a cubed RAB term in the denominator, and then another squared RAB term in the determinant of the correlation matrix here. So as your intermodal correlation goes up, this value, or the value in the denominator goes down, and so your test statistic would get higher for the same correlation between each of the models independently and the observations. That is to say that a higher intermodal correlation leads to a smaller, you'd need a smaller difference in skill to have a significant difference in skill. Okay, so this test was proposed specifically for the purpose of evaluating weather and climate model predictions in Siegert et al.'s 2017 paper, but the test itself is actually much older. So originally it was proposed in 1940 by Hotelling, and the version I'm showing here is a modification from Williams' 1959 to improve behavior over a wider range of input values. The test was recommended for psychological studies by Steger in 1980, and then suggested for basically the exact conundrum I've been having by Stefan Siegert and co-authors in 2017. And Siegert et al. Have done the hard work for me of showing that this test, which they labeled the Steger test, outperforms the standard test, which they labeled the Fisher test. So this figure, modified from their paper, shows that the rate of false rejection for the Fisher test essentially drops to 0 as your intermodal correlation gets higher. That is, the standard test becomes far too conservative as intermodal correlation grows. The Steger test, on the other hand, closely matches the false rejection rate for all values of RAB, which is the desired behavior. So, to test whether or not the SMILE and AR1 PDO predictions are significantly different for each lead, I can follow these steps. First, calculate the correlation between each model and the observations, which I've already done, and then calculate the correlation between each of the models. Then, with those values, I can calculate the test statistic and go get the critical t-value for whatever my significance level and number of samples is. So here, alpha 0.95 and 50 years for the SMILE ensemble. Then for a two-tailed test, if my test statistic is greater than the absolute value of the critical value, I reject the null hypothesis. I have a significantly different correlation skill. And this is what that looks like for this case. So here I've filled in circles for every lead at which SMILE predictions are significantly different than the AR1 predictions. And the results agree much better with my initial interpretation of this plot. So now I can say not that SMILE is substantially better, but that it is significantly better than the AR1 model from leads 4 to 13. And how does this look like for the other initializations? So starting with May, you can see that from leads 4 to 7, we have a significant improvement over the AR1 model. And this is in the boreal fall following initialization. In August, you have those same months showing up as significant, but they're at leads 3 and 4 rather than 5, 6, 7. There's also this period towards the end of the August initialization where you get significant improvements, and I'm not entirely sure what that's coming from, but it's in the spring, so it might have something to do with reemergence. Jury's still out on that one. But for the November initialization, there are 0 lead times where there's a significant improvement in SMILE predictions of the PDO over the AR1 process. And this is of particular note because the decadal prediction large ensemble is only initialized in November. But these results indicate that, at least for PDO predictability, November is actually the worst of these initialization dates to start at. And this result kind of reinforces what I was showing at the beginning of the talk. So not only does the November initialization struggle to predict the spring PDO index better than predictions initialized in February, but it also fails to outperform an AR1 model at all lead times. So in conclusion, today I showed a simple and effective test to look at intermodel correlation, and that it's important to account for this model correlation when you're looking at skill differences between models. On the science side, I showed that the SMILE PDO predictions outperform an AR1 model in February for most of the first year, but that it never outperforms, for the November initialization, it never outperforms an AR1 model. Pending a second review, these results will be available in my paper at GRO. These are my references, mostly for YouTube. And with that, I'll take any questions.
Ask a naive question since I'm not an expert in the PDO. Do you expect to be able to predict the PDO beyond an AR1 process? As in, is the PDO more than an AR1 process?
Yeah, I think actually just from the line that I'm showing here, you can see that it's more than an AR1 process because your expected prediction skill would fall as an exponential, and it's not doing that. So there's some seasonality there, and that's because there are more processes that are predictable that go into the PDO index. And that's kind of the reason that I was looking at this, was because the PDO, as the first pattern of variability in the North Pacific, is kind of encoding a lot of that information. And so this was kind of an idea to use this as a sort of proxy for North Pacific predictability in general. And yeah, like for the February initialization, as you can see, like it does better for quite a long amount of time.
Done a very, very careful job with looking at the correlations, and
Yep.
if I understood correctly, in space. Is that right?
This is the correlation of the PDO index. So I calculate the PDO index. Yeah, so I have the value, and I can project the PDO pattern onto each of the initializations, and then I get an index value at each lead time. That I have a predicted index value at each lead time, and then I can compare it to the observed value of the PDO index at each lead time.
Question.
Okay.
If you looked at the temporal correlations or just the spatial one. But thanks.
Yeah, this is very highly temporally correlated, which I'm showing by that alpha value there, which is part of the reason that you have predictability at such long lead times. So I haven't explicitly looked at that, but I think you could do that with an AR2 or AR3 model where you're including additional lead times and seeing how that improves your prediction.
And I'm just wondering if you think there's any reason to believe that a February initialization would give us better decadal skill. So November was chosen because but maybe PDO is more relevant for the United States. You can see that in February you have higher spring skill in year one, comparable skill in year two. Like, give us better decadal Pacific skill on multi-year lead times or decadal time.
Yeah, that's a really good question. This is mostly speculation, but if you are starting in February, you've basically given the model a whole winter to take whatever anomalies the atmosphere gave and have the ocean integrate that. And then you start at about the same time that the atmosphere is starting to put less information into the ocean at high latitudes. So I wonder if that is part of the reason you get such high prediction skill through the following winter. Versus November initialization, you're basically initializing at about the time where the mostly random atmosphere is getting strongest, and so the ocean is going to be integrating random information rather than the information from the observations.
All right, we now have a break until 3 o'clock, so please come back at 3 o'clock for a few more talks and some discussion. All right, in the interest of getting started on time, hopefully they'll also come inside. All right, our next speaker is Dylan Oldenburg.
Do you want me to already start? Oh, okay. Hi, so I'm Dylan Oldenburg, and I'm going to be talking about AMOC predictability in CMIP6 models today. Oh, the microphone. Can you, is this good? Do I need to lean in like this?
You might have to lean a little or move it up a little just so it'll catch you better.
Okay. All right, is this okay? All right, great. And so the goal in this work is really to analyze the AMOC predictive skill in different CMIP6 models. So the AMOC predictive skill in CESM DPLE has been linked to Labrador seawater thickness, propagating at depth towards the mid-Atlantic ridge, where these anomalies accumulate and then drive predictable decadal changes in the gyrocirculation, the sea surface height gradient, and the near surface circulation, accounting for skillful prediction of the subpolar North Atlantic upper ocean heat content. And so the question is, does this mechanism found in the large ensemble decadal prediction of CESM1, does that hold in other CMIP6 models that have similar decadal prediction systems? And then of all these models, do the models that have high AMOC predictability also show high predictability in the subpolar North Atlantic? Oh, whoops. Do models, with high AMOC predictability also show high subpolar North Atlantic upper ocean heat content predictive skill? And so the goals of this work are to determine the subpolar North Atlantic upper ocean heat content predictive skill in CMIP6 decadal prediction models. And so there are many models that have data here. These are from hindcast runs, run from about 1960 onwards. So there are runs that are initialized each year and then run for 10 years each, freely run. And they're initialized from assimilation runs or observations. And the data sets they're initialized from also vary based on the model. And so we determine whether, as I said before, the high subpolar North Atlantic upper ocean heat content skill can be linked to predictable AMOC variations. So does the mechanism found in Jaeger 2020, does it hold in other models that also have high skill? And so to do this, we compute the AMOC either at 45 degrees north in density coordinates, or if we can, so for some models, if we can, we will compute the full AMOC stream function in density coordinates and use that instead. And then compute the subpolar North Atlantic upper ocean heat content skill in the CMIP6 decadal prediction simulations. And then we'll do that skill based compared to relative to EN4. That's going to be our observational data set that we'll compare skill based on. And then do an EOF decomposition of the AMOC. So is the upper ocean heat content, subpolar North Atlantic upper ocean heat content linked to the leading modes of AMOC variability in the models that have high skill? And is that differing in the ones with low skill? And then also, do models with stronger biases in the North Atlantic have lower upper ocean heat content skill? So some models may be initialized from data sets that are not very good, and so that might just lead to the variability also being wrong. And so we use all the models that have available data for all the variables we need. So we have quite a few different models here. CAN ESM5, for example. We have some medium resolution models like HAD-GEM3. And then we have a lot of low-res models. There are some other models, but they don't have quite the length of the simulation that we need. Some of them are just just have simulations that are run to like 3 years rather than 10 years. And so the subpolar North Atlantic aberration heat content skill varies greatly across these models. So there's a wide range of skill amongst the models we use, which is what we want. So this will allow us to more easily determine whether ones with better predictive skill and the aberration heat content. So the definition of the subpolar North Atlantic region is this box here. And let's see, I can point at the box. And so yeah, we can more easily determine whether ones with better predictive skill and the aberration heat content also have better Mach predictability. So these show the anomaly correlations, and that's the mean of the anomalies of the hindcast relative to the model climatology. And so this is just distilling those into dots. So basically the aberration heat content skill in those boxes for each of the models for leads not 5 through 9. So smoothed over a 5-year lead time after the model simulations are initialized relative to EN4, that's our observational data set. And so we have a few high skill models. So the high skill models in this case are CMCC, CESM, CESM1 and CESM2, and then HAD-GEM3, the medium resolution. And then we also have some low skilled models. We have CAN ESM5, and then FGOLS, F3L, and then BCC CSM2 medium resolution. And then we have a bunch of models that are in between. So ones that have, I would say, are still fairly low skill, but some are kind of middling. Some of them actually just show the reverse of what we expect to find in terms of the variability. So it's interesting. And so another way to look at this is to look at the time series. So looking at leads 5 through 9 years. In this case, for one of the models that's considered to be one of the better ones with predictive skills, so 0.5 anomaly correlation. Yeah, so this is one of the good models, this is CESM2, the DP, the decadal prediction of that, the large ensemble. This one has, I believe, 40 members. And then this is one of the low quality models, CAN ESM5, which has variability that just doesn't have any alignment with EN4, with the observations. It's similar if you look at SST and compare to Hadley SST, for example. It just does not align with the variability at all. Even at low lead times, if you just look at like the year that it was even initialized from, it's already quite poor. So in terms of trying to link this to Mach, the question is, so is the skill linked to predictive AMOC changes? So unfortunately, we don't have the full Mach stream functions for every model, but we can compute it at 45 degrees north. But the problem is that first of all, we don't have a great observational data set to compute the skill relative to. I mean, we can compare it to high-resolution FOSSI simulations, but it's tricky because the structures are quite different. The maxima are located in different places, so it makes it a bit tricky to just compute the skill. So the maxima are not co-located, for example. And so because of this, we can do an EOF decomposition. So rather than computing the skill for Mach relative to the FOSSI reanalyses, we can determine the leading modes of variability and then see whether that's linked to the aberration heat content, the predictive aberration heat content variability. So this is one of the high skill models. So this is CESM1, low resolution. And so this is the first EOF for pretty much all the models is just a broad strengthening of AMOC. But what we're really interested in is what Steve Jaeger talked about in his 2020 paper, which is this mode of variability that's linked to densification of AMOC. And so that's what's shown here, EOF2, which represents about 15 to 20% of the variance in the data. And then so in CESM2, we can also see that this EOF represents, EOF number 2 also represents a densification. And then when we look at a poor quality model, this is one of the few poor quality models in terms of the aberration heat content that show what was I saying here? This is one of the few where we have the full stream function, I meant to say. So this shows a similar mode of variability, except this is actually the first EOF. So it represents about 75, it represents a majority of the variance in this model, which is sort of interesting. And for the low skill models, unfortunately, we just have, for now, hopefully in the future, we'll have the full stream functions, but we just have it at 45 degrees north. And they also exhibit a similar, some of them also exhibit a similar mode of variability where you have, let's see, can you see? Oops. What's happening here? You have like a densification, so a strengthening at the denser areas and then a weakening. So you see that in some of the models. And so what I need, what the next plan is to try to correlate these, see whether there's a correlation between this mode of variability and the upper ocean heat content variability. But I haven't quite done that yet. I'm still working on that. And in terms of the biases, this is the upper ocean heat content subpolar North Atlantic bias. Leads 5 through 9 years versus the upper ocean heat content prediction skill over that same lead time. And so there isn't really a clear, oh, whoops, sorry. Hang on. Yeah, so this is what I was talking about. But there isn't really a clear relationship. There are some that have fairly good anomaly correlations, fairly good predictive skill, but have quite large biases in that region. So the question is, and it's the same if you look at the upper ocean salinity. So basically, the bias in the upper ocean salinity versus EN4. And so the question is, maybe the control of the predictive skill is actually just actually linked to biases in a different region rather than the actual local bias in that subpolar North Atlantic box. Yeah. And so the next step is to determine the link between the leading EOFs and the subpolar North Atlantic upper ocean heat content predictive skill, and then to look at different regions, try to determine whether biases in other regions are really causing the problems with the predictive skill of the upper ocean heat content. And that's it.
The EOFs are going to prioritize maximizing variability in the overturning stream function. But it could be that there is some strong correlation between upper ocean heat content and some other structure that maybe is a mixture of the EOFs. I was wondering if you tried even just like regressing upper ocean heat content onto the stream function to try to discover structures that might be predictable.
That's a good point. Yeah, I will also consider doing that. I'm still working on how exactly to. I was still working on how exactly to do the correlation. But yeah, that's a really good idea. Thank you. Hi.
Yes, as I remember Steve's paper in 2020, there was a whole line of processes in the mechanism to get you from upper ocean heat content to gyre spin up to predictability. And I was wondering, do you have any plans to look through the rest of those pieces beyond upper ocean heat content and trace that out? And what would the next pieces then be in that mechanism?
Yeah, looking at kind of the propagation of that deep, dense water, and then also, yeah, looking at the Labrador seawater thickness. Yeah, the plan is to kind of see whether that full mechanism is. This is just kind of the starting point of that. But yeah, to look at that full mechanism, just as you said, and see whether that holds in these different models, at least the ones with high skill. Yeah.
I was wondering, it seems to me like you're trying to find patterns that maximize skill. And it came to mind to me that maybe canonical correlation analysis might help. It's basically, I'm not sure if you're familiar, it's okay if you're not, but it's like EOF analysis, but instead of maximizing variance, you're maximizing skill, and so you get leading patterns associated with skill, which might be useful for what you're trying to do.
Thank you. Okay, yeah, I'll look into that. Thank you.
Our next speaker is Jerry Mule.
Thanks. This is a title is a little bit different from what's in the program, but the topic is pretty much the same. So this all starts with a very large wildfire event in eastern Australia. Started in late 2019, went into early 2020, produced massive amounts of smoke that made it across the Pacific. And John Fasulo had a paper in 2023 where he showed that this smoke could actually affect the onset of the subsequent La Nina event. And just to recap those results, basically it starts here with the smoke in Australia. It makes it across the subtropical Pacific, doesn't get rained out, brightens the clouds off of South America. The brighter clouds reflect more sun. That means less sun gets to the surface. The SSTs cool. The cooler water makes its way up into the eastern equatorial Pacific. And Bjertnæs feedback spread the cool SSTs out to the central equatorial Pacific. So that was kind of the starting point of this. And what I'm going to be talking about today are what processes and mechanisms sustained that La Nina event for 3 years, because it went on for 3 years, which was kind of interesting. So we did 2 sets of initialized hindcasts in a little bit different ways. We did these initialized hindcasts as a sensitivity experiment. So we ran one set, the standard SMILE hindcast for 3 years, initialized in August 2019. Then did another set, initialized at the same time for the same 3-year period, but just included the effects of the observed Australian wildfire smoke from GFET. So the set without the Australian wildfire smoke, we call these standard SMILE, or the no smoke experiments, and the set with the observed Australian bushfire smoke emissions from GFET are the smoke experiments. And the thing about doing it this way is that you can look, because you're only changing one thing, you're only changing these smoke emissions. By differencing these 2 hindcasts run over the same period identically, anything that's different in those 2 are from the effects of the wildfire smokes. You can actually try to isolate, at least in the model, what the effects of the wildfire smoke were. And the other advantage is by differencing these sets of, the same set of hindcasts over the same time period, by doing the difference, you remove the drift identically. It's the same drift over the same time period, so you don't have to worry about drift adjustment. So what happens is, if you look at sea surface temperature anomalies going for the CSM2 on the left and the E3SM version 2 on the right, years 1, 2, and 3 are the 3 rows there, starting in August 2019 to 2020. These are annual means. And you can see that in both the models, in the first year, as was documented in John's paper, you see this cooler SSTs forming. Then in year 2, in CSM2, you can see that the cooler SSTs are spread across the Pacific, same thing in E3SM. And by year 3, it's maybe even stronger in CSM2, and also maybe a bit stronger in E3SM. A couple interesting things. First of all, both models sustain this La Nina event, just associated with the effects of the wildfire smoke for 3 years. But of course, the wildfire smoke is gone by March of 2020. So something else is keeping this going in the 2 models. The other thing is that you can see just by eye that the amplitude of the anomalies in the CSM are about twice that in the E3SM. And the reasons for that are several possibilities. We're still looking at exactly why that should be. Okay, so what's doing this? So hang on, we're going to go through a couple of feedbacks pretty quickly here, and it's a little bit complicated, but it hopefully will make sense, and I'm going to recap it in a couple different ways at the end. So we can start out, these are year 3 differences now, CSM2 on the left, E3SM2 on the right. The top row is precipitation for year 3 differences, and you can see, as you can expect, because this is a La Nina event in year 1, you get reduced precipitation over the cooler water, and because during La Nina events you're pushing the stronger trades, you're pushing the warmer water over the maritime continent and the western Pacific. That's warming things up over here and producing stronger precipitation over the maritime continent. You see that in both models. And of course, associated with those changes in surface temperature and precipitation, you'd expect to see lower sea level pressure over this western Pacific area, which you get here. The blue colors here are lower sea level pressure in the smoke experiments. That's in both models. Again, stronger amplitude in the CSM. And because you're getting the stronger precipitation over the maritime continent, that means you're getting stronger upward vertical motion, stronger upper level outflow. That stronger upper level outflow is going to descend in the eastern Pacific and strengthen the subtropical high. And so you see this, and looking at the 200 hectopascal velocity potential, indeed you see these negative velocity potential values means stronger upper level outflow in both models. And this upper level outflow that comes down and descends, and you get these upper level convergence over the eastern Pacific, and those are the positive values over here. Okay, so that's kind of the starting point of what maintains it, but then the question is, what is causing some events to make it to 3 years and other events not to make it to 3 years? So it turns out Bjerknes feedback is the big story that maintains it, and so we thought that was the case, obviously, because we saw that with the spun up Walker circulation, it's very strong. Once you get the Walker circulation going, it's going to keep going unless something makes it stop. And so we wanted to figure out if any of these ensemble members actually stopped after 2 years and didn't go on to 3 years. So what we did is we came up with the indices. We had a Bjerknes feedback index, just zone surface wind stress anomalies across the equatorial Pacific, and a west-east SST gradient, basically western Pacific SST anomalies minus eastern Pacific. Plotted those in this top plot here as a scatter plot, and as you can imagine, it lines up pretty good for both models. In other words, when you get the stronger Bjerknes feedback, in other words, stronger trade winds, you get a stronger west-east SST gradient because you're piling up that warm water in the west. It's going to be cooler in the east. But the interesting thing that came out was we thought that we'd have that almost all the ensemble members, and each dot is another ensemble member, we thought they'd all be kind of clustered down here, and that the weaker events that were kind of fading out would all be kind of just weaker La Niñas. But actually, there's a number of events that actually transition to El Nino, and that's these events or the ensemble members up here in the upper right-hand quadrant. So when you look at the distributions across these, as you can imagine, because the ensemble average of the 30 ensemble members gives you this multi-year La Nina, when you do this binning based on Nino 3.4, these are La Nina events to the left here, El Nino events to the right, you get a preponderance of ensemble members that are giving you a 3-year La Nina event compared to El Nino, but some of these are actually transitioning to El Nino. So the question is, what's producing this transition in some of these ensemble members, and why do some of the ensemble members keep going into a 3rd year? So what we did was we composited the 5 strongest sustained La Nina events from that scatter diagram, and the 5 strongest curtailed events, or in other words, the El Nino events that ended up transitioning after the 2nd year. So in this plot, we've got these 2 boxes. The CSM2 is at the top, E3SM is at the bottom. This column on the left is the sustained events that went on for 3 years. The column on the right is the curtailed, or the ones that transitioned to El Nino. And we're looking here at year 2 and year 3 in both models. So year 2, the first thing you see that's different between the two is this area here in the north central Pacific. The events that transition to El Nino have a positive North Pacific meridional mode, and the ones that continued have a negative North Pacific meridional mode. In other words, these negative SSTs are kind of arcing down here from the North Pacific near Hawaii and getting into the central Pacific north of the equator. And you can see this in both models, right? So in both CSM and E3SM, you see that the ones that transition have this positive North Pacific meridional mode, and the negative for the year 2, and the year 2 then stays as a La Nina, and year 3 then they transition to El Nino. So that's kind of interesting. So that's apparently something going on there in the North Central Pacific with this North Pacific meridional mode seems to be playing some kind of a role. So what role could it be playing? Well, let's look at precipitation now for the 2 models, and this is for year 2. This is the curtailed events, and of course, as you'd expect, when these warmer SSTs are up here from the positive North Pacific meridional mode, you see enhanced precipitation. These red colors are enhanced precipitation, and the events that transition, the events that don't transition, you don't really see that, and you see it in both models. See in E3SM, you also see this enhanced precipitation over here. And of course, if you get enhanced precipitation over the warmer SSTs, that's going to be stronger upper vertical motion, stronger upper level outflow. And you're going to have some effect back over to the west, and you're probably going to get some descending motion over here in the west in the maritime continent, and that's kind of what you see. So if you look at 200 hectopascal velocity potential, you can see these negative values here over the warmer water and the stronger precipitation where the positive NPMM is, and you see a negative, still negative over here in the ones that are sustained into the third year. And you see that you're getting some anomalous descent, which you're weakening the anomalous low pressure north of the equator here, while it's really still strong here. And the same thing over here. So you're weakening the sea level pressure, you're getting more descent over the maritime continent there just from this anomalous Walker circulation that's instituted by this North Pacific meridional mode. And of course that then has implications for sea level pressure, as you can imagine. So the sea level pressure, when you get this kind of stronger precipitation and lower and positive SSTs, you get anomalous low sea level pressure here, which are the blue colors. And of course then you're going to get some anomalous westerly anomaly winds to the south of it. You can see these little vectors kind of turning around there. You see this in both models, right? You see this anomalous low with the kind of weakening of the strong trades. That's the one thing that happens. The second thing that happens is because you've got this kind of anomalous descent over the maritime continent, you're weakening this anomalous low pressure on this side. It's still strong over Australia. We still have this strong Walker circulation going on in the southern hemisphere between Australia and the southeast Pacific. But now you get somewhat weaker low pressure, anomalous low pressure, and that gives you an anomalous meridional sea level pressure gradient, which will give you anomalous westerly surface winds, which I've highlighted here with this black arrow, because the little arrows are kind of hard to see. And you see that in both models. And so, of course, when you get westerly anomaly surface winds, and especially weakened trades, that means you get downwelling Kelvin waves, you deepen the thermocline, the SSTs warm up, and you get the transition. And you don't see that in the ensemble members that are sustained. So let's go over this once to summarize it, and I'll say it again in a minute. This is a schematic. So the top here is the kind of the onset, which I was talking about with the wildfire smoke that gets this going. In the ensemble members that are sustained to 3 years, you basically get this Bjerknes feedback, coupled feedbacks going, where you get this stronger trade winds, get stronger upwelling, push more heat into the Western Pacific. That warms up the maritime continent and Western Pacific area. That gives you stronger precipitation, lower sea level pressure. Stronger precipitation gives you stronger upper level outflow, stronger descent over the Eastern Pacific. Subtropical high strengthens. That gives you stronger trades. Stronger trades push more water over, and it just goes in this feedback loop, the Bjerknes feedback loop. And this can go on indefinitely in theory unless something happens to make it stop. And in the ensemble members where it stops, this is what's happening, at least in the models, is you get a positive North Pacific meridional mode. You get positive SSTs over here with anomalous low pressure, stronger precipitation. Anomalous Walker circulation gives you some descent over here over the maritime continent, which weakens the anomalous low pressure. Low pressure is still strong over Australia, so you still get the strong Walker circulation between Australia and the southeast Pacific, but now you get this kind of anomalous weakened Walker circulation coming the other direction. This gives you an anomalous meridional surface pressure gradient, which contributes to westerly anomaly surface winds, as well as the anomalous westerlies that would come in from this anomalous low out here in the central equatorial Pacific. Okay, so let's skip that, and just to summarize this one more time. So it's been shown that smoke from the Australian wildfires contributed to the initiation of this multi-year La Nina event. The main process that sustains the event is Bjerknes feedback. It connects strong trade winds across the equatorial Pacific. That acts to cool tropical Pacific SSTs. That warms sea surface temperatures to the west, increases precipitation in the Western Pacific, and that gives you stronger vertical motion and stronger descent in the subtropical high in the Eastern Pacific through the Walker circulation. And that just kind of is a sustaining feedback set of processes. But then processes that can end this, that can change this, break this kind of chain of coupled feedbacks, is if a North Pacific meridional mode forms in the north central Pacific. That results in anomalous low pressure in the north central Pacific with westerly anomaly trades, as well as this altered Walker circulation with a weak and low pressure north of Australia. That gives you an anomalous meridional surface pressure gradient, westerly anomalous surface winds in the western equatorial Pacific, triggers downwelling Kelvin waves, and transitions to positive equatorial Pacific SST anomalies. So I hope you got all that. Thanks.
Thanks, Jerry. That was awesome. Did you say why for the members that did not have a sustained La Nina in the third year, why they had the warm PMM in the first place, or is it just chance?
Well, you know, you look at the literature on this these specific meridional modes, and you may have looked at some of these too. And the best you can get out of it is that it's kind of randomly generated. There isn't any evidence that these meridional modes are generated by any kind of tropical teleconnections. They seem to be somewhat stochastic in nature, and that seems to be the case here, that some ensemble members just get them, they start out, and but more ensemble members keep it going out to 3 years. So I think the nature of and I didn't say anything about the South Pacific meridional mode, which is actually helping to keep it going, because you see that is really strong in the South Pacific. So I think the role of these meridional modes, there's literature that shows how they are connected to ENSO in various ways. But I think that's a real interesting area of research that it'd be interesting to kind of learn more about exactly what causes them, how they set up, and what sustains them.
The E3SM versus CSM results look quite different.
Yep.
Even in the local features that you were saying that they are similar, they are actually different. And then given the larger scale differences, aren't they going to actually impact all of these mechanisms differently in both models? And then, I mean, I guess, have you done a budget analysis of some sort to verify that mechanism is actually going on?
Well, the thing that was, when you look at the ensemble averages, you know, the signal in the ensemble averages in E3SM is so much smaller than E3SM is smaller than CSM. When you look at these composites of the 5 strongest and 5 weakest, that's when you really see that they're really similar between the two models that are transitioning to El Nino versus La Nina. Both of them have these positive North Pacific meridional modes. Yeah, they're local, but that causes these large-scale features, because once you start changing something in the tropical Pacific, then that affects precipitation, water circulation characteristics, and that can really change the way this works. And so that was when we were looking at why some of them transitioned, others didn't. The one thing that seemed to be different was that North Pacific meridional mode. So I think that's a really important part of the story.
Nice talk. Maybe I missed it, but what are the wildfires' role in the multi-year event? Like, all the mechanisms later made sense, but that's probably a chance for any La Nina event to sustain itself, right?
Good, yeah. Yeah, and there's, of course, multi-year La Nina events. There's been previous 3-year La Nina events, but I think there's been a lot of literature trying to figure out what sustains some of these La Nina events for 2 or 3 years. In this case was interesting because it looked like one of the triggers was this wildfire smoke, but then the wildfire smoke goes away, and then once it's going, then it kind of keeps going. And so that was kind of what led us down this road to see. And that's, you know, these are sensitivity experiments, right? So you're just looking at the effects of the smoke. So definitely without the smoke, the model wasn't getting it. So, but I think once the model got going, and then it just kept going, and enough of the ensemble members sustained for 3 years that, you know, it came out in the ensemble average. But then looking at these ones that transition, because that's the thing that kind of surprised us. We thought, well, it'll probably be the ones that were weaker, you know, they'd all be kind of La Nina-like, but they kind of, some would be really weaker, but some of them really transitioned to El Nino. And that was kind of interesting.
A really interesting talk. And I'm really interested in the effect of the meridional modes into the far western Pacific through the outflow. I also know that they can have an influence when they reach the equator, which would be more in the central Pacific. So I was wondering if you have any plans to look at, like maybe looking at some Hofmahlers and see whether or not you see influence in the far western Pacific versus the central Pacific at that time, to see what, like, the relative importance of those two mechanisms that can feed back onto ENSO. Yeah,
and you're right about this Western Pacific connection. This has always been a thing about these meridional modes that I've never really understood, because, you know, they talk about in these papers you read, they're kind of coming down across Hawaii, but actually they just kind of set up all the way across to the Western Pacific. It's not like you can see them really propagating. So I think that's a really good point, to try to figure out, you know, how they connect to the Western Pacific, because that's what they're doing in the model. So if they're in the model, we should be able to analyze it. So I think that's a good point. Yeah. Yep.
All right, our next speaker is Steve Yeager.
Okay, so I'm going to follow up from Judith and talk about this elephant in the room that we all know is there, but we try to sweep it under the rug, which is drift in initialized Earth system predictions. And I'd like to thank all the people I've been working with on this topic. really started thinking about this more when Xian Wu was an ASP postdoc here, and it's kind of the culmination of that effort. So model bias poses challenges for initialized Earth system prediction. This figure from Jerry's review paper gives a nice visualization of what we're talking about here. So models are initialized from some observed trajectory in the black line, and these hindcasts drift away, and that drift is a function of lead time, and it sort of asymptotes towards this systematic model bias that you can diagnose from a coupled model simulation. But it doesn't go directly there. There's some overshoots, right? And so this unrealistic drift signal complicates comparison of uninitialized predictions with observations. And there are a number of effective methods to de-drift, reforecast to enhance prediction skill, from simple to very sophisticated, right? So that's part of the calibration of prediction systems, is removing this, recalibrating the variance of your ensemble. And that's not really the topic of this talk. The topic of this talk is the significant expense of those methods. They inhibit experimentation. What we'd really like to be able to do is do initialized prediction case studies and explore this full kind of phase space of perturbations we could make to physics, resolution, parameters, initialization. Like, we want to be able to experiment with initialized predictions, not just recalibrate this expensive set of predictions. So that's the topic of the talk. And I just want to start with this, this simple example. This is taken from a decadal prediction system using CESM1, but it would apply to any time scale from subseasonal to decadal. So what we have here is observations in black, in quotes, with this very abrupt signal in the mid-90s, this famous mid-90s warming. And then we have some historical ensemble from a coupled simulation, in this case CESM1. And we compute anomalies, and that's how we compare our model with observation. So the observed anomaly is just subtracting a climatology, and the historical anomaly is subtracting the model climatology, right? So you can get rid of the bias, and you can compare them in terms of anomaly. So let's imagine that we wanted to do a prediction case study of this event with our brand new model. We wanted to see, is this going to be a good decadal prediction model? So what we might do is we initialize from observations, and we only have this one little case study. So what are we going to do? How are we going to compute anomalies? We could compute anomalies from observed climatology. After all, we're starting the model from observed conditions. So this is what we would get, and we would say, this is a crap system. Like, this is not a good prediction system, right? And of course, that's not true. Most of the signal you're seeing here is drift. So how do we get at that? So this is method one. I'll refer to different methods. Method one is you assume the model has no bias, no drift. And of course, a pro of that is it's a very cheap method. But the con is it gives poor results when you're initializing a biased model from observations. So what we normally do in the initialized prediction world is we conduct a large set of reforecasts to estimate the model drift. And that is computed in this fashion. We have many different reforecasts that are a function of lead time tau that verify at a certain time t, and we do this with many members. And then we take the average evolution as a function of tau, lead time, over some climatological window where these forecasts are verifying over our whole ensemble member dimension. And this is what we call the model lead time dependent climatology. And it's a function of tau, and that's what we mean by drift. When tau is small, this forecast climatology is like observed. And when tau goes to infinity, we're asymptoting towards the model systematic climatology. That's drift. How can we estimate drift is the question here. So we normally do it this way, or at least this is the most common method. As I said, there's more sophisticated ones, but this is what we do across timescales. We compute this model lead-dependent climatology from our set of reforecasts. We compute forecast anomalies from that climatology. And this is simple. As you can see here, it's effective. In fact, this is a quite skillful decadal prediction system. That case study does predict an abrupt shift in North Atlantic upper ocean heat content once you perform this de-drift step. But the con of this method is that it's expensive. We have to do all these reforecasts. It's very labor intensive, definitely not good for initialized prediction case studies. So let's talk about efficient drift estimation. As I said, one option would be to use a companion uninitialized historical large ensemble to compute forecast anomalies. This is take your forecast and subtract, your systematic model climatology. And Jerry has written on this. This is a viable method. It's definitely promising for decadal forecasts when the drift has asymptoted for a large tau, but it's not good for short time scales that are sort of mid-drift. And it's not good for sensitivity case studies because you don't have an uninitialized large ensemble anyways. You've got some new system that you want to test out. So another option could be to use method 2, do a reforecast set, but with a really small ensemble size, right? So the expense of this method 2 is going to depend on M here. How many members are you going to include? And you could decide to include only a very small number of members. And then another idea that Xian Wu used in her recent 2024 paper, where she was looking at these decadal prediction case studies with initial conditions only in certain regions of the globe, and we weren't sure, well, is that going to affect the drift? Well, let's run a CLIMO-IC ensemble where we initialize from climatology everywhere and kind of use that as a de-drift method. So that's the idea here, is we're going to initialize the model from climatological atmosphere and ocean initial conditions, but we can't do that with the land and ice models from CESM because they blow up when you try to initialize them from a climatological state. So what we did in this paper and what was also done in Yaga's paper is you pair climatological atmosphere and ocean with a collection of land and ice states from n different individual years. So you kind of got this mismatch, right? That's what we call CLIMO-IC. And Xian Wu showed that it works really well. It kind of gives you the same answer as you would get if you had a full reforecast set. So we didn't actually have to do the CLIMO-IC experiment, but we didn't know that. But the fact that CLIMO-IC kind of gives you the same answer as method 2 suggests that that could be an efficient drift estimation method. All right, so this talk is going to focus on these two ideas, small reforecast ensemble or CLIMO-IC. And we're going to leverage this large reforecast set that we have that spans timescales from subseasonal through seasonal, multi-year, all the way out to decadal with large ensembles. And we're also going to throw into the mix the E3SM v2.1 SMILE that we have. And here's kind of the key point, which is the cost. If you use method 1, so you assume the model has no bias, then there's no cost, but it's not very good. So method 2 is standard, and the cost of that method is going to depend on the M that you choose, the number of members. So you can do the multiplication here. For S2S, it takes about 220 simulation years to estimate S2S drift. And method 3, which is this CLIMO-IC method, is only a function of how many members you include. So it's already, you can see, potentially cheaper than method 2. And then this is how we're going to quantify it. We're going to say if this alternative drift or lead-dependent climatology is similar to what we get with method 2, that means we've got a good answer. But we need to quantify, like, what does similar climatology mean in a more rigorous way. So we're going to use this mean square skill score, where here we're measuring the distance of our anomalies computed using an alternate method compared to method 2 anomalies kind of normalized by method 2 variance. It turns out that if you do the math, this is the difference between the climatologies that you estimate, kind of normalized by expected variance of a field. All right, so some results. So this is what S2S SAT, surface air temperature bias, looks like in the CSM2 system for winter and summer initializations as a function of forecast week. This is something that Yaga has shown in her papers. Clearly very rapid bias development even in week 1. There's some growth of bias with lead time, you can see by eye. And seasonality too, very different in winter and summer. And I was going to point out here the color scale, -5 to 5. I'm going to keep that same color scale. And now I'm going to show you the difference in SAT climatology using alternate methods compared to this best method. This is what we use in papers, right? Method 2. So method 3 is the ClimOIC, and what you see is pretty large differences that really start to pop out in forecast week 2 all the way out through 4. Maybe not such a good method for sub-seasonal. It's on the same scale, so you're getting errors in the climatology that are of the same order as your climatological bias. That's one initialization with 22 members. Method 2 with 1 member is the same cost, but we get a much better estimation of the drifting climatology. So at least for sub-seasonal, it seems like this kind of low ensemble method 2 could be a viable method. Of course, as you increase the ensemble size, you get better and better, right? So you can always do better if you add more members, but even with 1 member, you're doing a pretty good job of estimating climatology. And then that translates into differences in skill score. So method 1, assuming no model bias, is not a good method. Method 3, shows these problems, particularly over North America and Canada. Method 2 with 1 member is pretty good. And I would say that this is a viable method for sub-seasonal prediction case studies. And then, of course, it gets better as you add more members. All right, now we're going on to seasonal timescales, and we've got 2 systems now. And I'm showing you the mean model bias as a function of forecast lead time. Clearly very different in these 2 models, and it's also a function of forecast year, so it doesn't stabilize for some time, and that's something that Jerry has shown in his papers. If you try alternate methods, this method 2 with 1 members is showing quite good skill for both systems, suggesting that this is a viable method to do efficient drift estimation, even on seasonal time scales. And then let's put this into practice. Like, what if we wanted to do an initialized prediction case study for 97, 98 El Nino? With CESM2, we've got this red curve, which is our standard method. It's quite expensive. And this is what we think of as the true forecast anomaly. Method 1, not giving us good results. But these alternative methods are actually giving us very good estimation of the forecast anomaly for this event all the way out through 24-month lead times. And they're also working in this other system, although this method 2 1 member isn't quite as good with E3SM, and that may be because it's got more ENSO variance. I'm not sure. So whenever you've got more variance, you need more members to beat down that noise. All right, and very quickly, it also works on decadal timescales. So you do this 30 initializations with 1 member, and you get a very good estimation of your decadal annual surface air temperature bias. So this is kind of interesting, though. To do decadal prediction case studies, it looks, quite viable that we can get the same result as RED, which, as I said, is our true current method, using this method 2 one member, which is 1/20th the cost of doing a decadal prediction case study, and we're getting, indications that CSM2 decadal prediction is good at predicting this rapid warming and this rapid cooling in the subpolar North Atlantic. It's also showing decent skill at getting these IPO phase transitions that Jerry has highlighted in his work, right? This change from negative to positive and then positive to negative, and we can do prediction case studies like that much more cheaply than we have in the past. So it looks like efficient S2, S2D forecast drift estimation shows promise here, benchmarked against conventional techniques using full reforecast sets from both CSM2 and E3SMB 2.1. Indications are that both ClimOIC and this one-member method 2 work well for S2D at a small fraction of the standard cost, but initialization shock makes ClimOIC problematic for S2S. I didn't show the shock, but I'm happy to share that if you've got questions. And so these results can inform the use of initialized prediction framework for model development, testing initialization methods, etc. And in fact, we're doing that right now with the CSM3 model. And I included this because I made this plot during the high-res session this morning, and I thought it was cool. So we've almost completed this full set of CSM3 initialized predictions using this one-member method 2. So what we did is ran 62 sim years in total, all run in parallel, so quite cheap. And what we see is for this 97-98 event, CSM3, showing actually a really good El Nino decay phase. It gets into the La Nina, but it doesn't sustain the La Nina as much as we would like. And it suggests, maybe there's some coupled feedbacks here in the summer of year 1 that are to blame, that it's just not maintaining that La Nina to the same extent that, for example, CSM2 did. So potential, for using this in practice. Thanks. I don't know.
Maybe less of a question, more of a comment. Maybe a fourth method worth highlighting is model analogs here again. I know we talk about this a lot, but that's one huge advantage of analog forecasting is you don't have to worry about the drift part. It doesn't work for all contexts and all timescales, but it could probably be competitive to one of these methods on seasonal and decadal. Well, maybe not decadal, but certainly seasonal, and I think we've talked about that before.
But how could you use an analog to get the drift?
You don't need the drift. There's no drift. You're already in the biased model state, so you don't have to worry about the drift part. So you don't have to, there's nothing to fix because you're already in, you're at lag infinity.
You can't do analog unless you have a huge library. So what would you do with CSM3 that's in development? Like, that's the whole conundrum, right? We have a new system that we don't have all of these simulations to utilize, but we want to test the predictive skill of that system.
Yeah, when you don't have a library, then you have to lean on these other techniques. But there's a huge initial cost to the analog forecasting because you have to build the training data set. But yeah, thank you.
When you showed it, I think in method 3, big biases develop over the land, and I forgot what you said you were doing with the land in method 3, but does that tell us anything about these issues that we have with the land not leading to skill?
I think so, but I don't know. So what we're doing is with these CLIMO experiments is we're pairing a climatological atmosphere and ocean with a non-climatological land and sea ice. And as you might imagine, they're not in balance, and we get initialization shock from that, right? And, you know, I don't, this was a plot I put in the extra, but, you know, how do we quantify initialization shock? And I've tried to do it this way. So I was looking at this one grid point over Canada, and if you look at the growth of ensemble spread in these CLIMO IC experiments on S2S timescale, so as a function of forecast day, you get this huge growth in spread. So you've got this hugely spread ensemble, and the spread like goes outside the bounds of the spread that you expect when you like pair component initializations that are at least in better balance. So it's like, you know, I think any signal that you're getting from a really spread ensemble is inherently uncertain. You know, so I think, you know, this settles down eventually, but I think on these subseasonal timescales, you could be getting initialization shock effects, basically.
I think we should move to the co-chair update.
Yep.
And we're going to be a little short on time for discussion. So Steve's going to talk about some of the different kinds of experiments that the Earth System Prediction Working Group has. And if we don't get a chance to talk too much about them, we would really appreciate hearing any feedback you have on which ones you find useful, how you might use them, and things of that sort.
Yeah, sorry for going long. As always, wanted to bring the working group up to date on data sets that we have that are available. We've got these S2S experiments that we've heard about from Yaga's 2024 paper that are available. We've recently backward extended CSM2 SMILE, so now all these initializations go back to 1958. So that's a new development. I've mentioned before in past meetings, we've done these SMILE, CLIVAR, TBI coordinated experiments. So these are hindcast pacemaker experiments that are equivalent to SMILE, but with regional SST nudged to observations in the tropics of each different ocean basin. And there's now a paper out in GMD describing those experiments. CSM2DP has been available for a while, but one new development is that we're processing the time series files and getting those uploaded to CMIP6+. So that will probably be the easiest way to analyze this data set unless you're sort of an expert, because these will like already be in time series format. And then we've completed CSM2 multi-decadal predictions. So these are basically an extension of CSM2DP every 5 years, and these go out 20 years. So we can look at, you know, do we get initial condition predictability on these multi-decadal timescales? So super briefly, ongoing and planned allocation usage. You can see the ones that we've already completed, and then a list of, you know, kind of ideas for how we're going to use up our allocation in the remaining, I guess, year and a half that we have. So you can read through those various timescales, including now CSM3 case study experiments. And I just gave you an example. I think we're going to be doing more of that. And maybe once we get a configuration that we like, you know, put CSM3 to the test on these short timescale predictions. And then I just wanted to advertise this this open workshop that will be happening in November in Italy, but a hybrid option. So if you're someone who's interested in annual to multi-decadal climate variability and predictability, please consider submitting an abstract. Deadline 15th of July. So I think that was it, and now we can open it up to discussion for maybe 5 minutes.
I'll highlight the S2S Climo initialized experiments. We've heard a lot about those today. I'm finding them personally very useful in understanding sources of skill and trying to get at predictability. So if there's others who are using that or want to use those, maybe don't quite know how to get access to them or what to do, you can feel free to contact me. Steve, if you'll put that last slide up, just because it has contact information on it.
The last slide?
Yep,
Oh,
the last slide, yes. So, oops, that's the wrong contact information for me. It is kpijon@ou.edu. I've changed institutions. But feel free to contact me if you have interest or would like to get access to those and maybe don't quite know how to get into those. And we welcome any other thoughts about the data sets, things you'd like to use, obstacles to accessing them, anything of that sort, experiments you would like to see. Quick, you only have a few seconds to tell us your experiments you want to see.
I was wondering if you had any plans to, like given all the talk about AI/ML that's going on, are there any plans to try to use that in some way for prediction in this working group? Or is that happening elsewhere, or is it not happening? I guess.
I mean, that's happening definitely at NCAR, and Will Chapman and Judith Berner have sort of ML-based parameterizations that they're testing out in S2S framework, so I don't see either of them here, but yes.
Okay.
I think that's a fair question. I mean, I don't know the answer to this. Is there an effort around a machine learning version, AI version of CESM? I would love to see some of these machine learning emulators run like following the reforecast protocol that we could evaluate consistent with other reforecasts would be amazing.
All right, if no other, or Dylan, you want to take the last word?
I feel like I bring this up every year, so I might as well do it one more time. Any plans down the line for a higher resolution initialized prediction system in CSM3? Like, I think we've talked at some point about like nested high resolution grids with initialized prediction, or something in the Mesa Clip domain for very limited time periods.
Point 3 Mesa Clip decadal predictions, and in addition to what Steve led, so we have now 1980 filling it every single year all the way to 2024, well 2023 I guess. Ensemble members each, 62 months each, and 2 start dates per year, November 1st and May 1st. So the ones that in Steve's paper, all those simulations are available, but they're every other year and November initialization. So now we are doing it from 1970 or 80, I think, 80. And so they will be available as soon as the simulations are still running. So there is actually a decadal, 62-month equivalent of some of these simulations with CSM 1.3, and we have plans to run when the CSM.
All right, let's thank all our speakers and thank you.